Okay, sorry everyone for the delay. The line in Engineering Cafe was like 50 people long, so again, my apologies. So today we're going to be doing, you all notice we're here instead of the SIG lab. We're going to be doing a continuation of like the stuff we covered yesterday. Trung was in the middle of lighting models, so we're going to talk about the topics you see on the screen. But first, I want to check to see if anyone has had any issues with the homework. There were a couple questions on transformations, and there's definitely some of those things that you shouldn't have been able to answer given just the information in Tuesday's lecture. So my hope is that today we can clear any of those questions up. We're going to go in depth about what an actual transformation matrix looks like, because yesterday I glossed over it. And yeah, so before we get into some basic review questions, does anyone have anything they want to ask first? Sure.
So when you say transformation matrix, you're talking about like the diagram in question one?
Yeah, I think there's two, right? There's another. Yeah.
Okay.
Is there a question behind?
Yeah, I was going to say, so you said you can put the lines on because of copyright stuff. Is it possible to put the few slides where you went over transformation in like more detail?
Yeah, no, we can do, Emily's actually going to do like a full transformation thing in a couple minutes, so that's definitely happening. Anything else before we kick off a couple of review questions? No? Okay. Trung, do you want to come up and do some review?
Yeah.
So I think what we wanted to do was spend a couple of minutes kind of asking some questions about the stuff we covered yesterday to see if it actually sunk in and to make sure that everybody's kind of on the same page. So you can jump right in and we'll intersperse some questions from my stuff.
Okay. I'm just going to do the light part.
Sure.
So there is... So we went through lights yesterday. Okay. Just really quick. Okay, so in this image, can you guys name some lighting effects that you see? Just anything on top of your head. Okay.
Area light.
Area light, yep. Yeah, that's called area lights.
It's a good start. Anyone else? Objects. Look at the way the light is bouncing. Sorry? Refraction, okay.
Yeah, the buttons have like a refractive materials, kind of glassy and stuff like that.
Anybody else?
Reflection.
What?
Reflection?
Reflection? Yes. Where is the reflection?
Like the bright parts around it.
You mean like these part right here?
Yeah, like up the top.
Yeah. Okay. So yeah. So these are specular from the light. Do you guys want me to turn up the light and put back if it's possible?
Is there a way to get the light from the projector off?
Oh, let me see. No.
Well,
Make it
okay.
easier to see. Yeah. Anything else you guys see?
Can you guys call about like when the color from a wall is like bounces off?
Yeah.
There's like a little bit of blue.
So like this part right here,
Yeah.
on the side, a little bit blue on the white background. Anyone remembers what it's called? Yeah.
There you go.
It's called glow illumination. When you see that sort of color bleeding effect, so like from this red wall to this white wall, same thing with the blue right here. And they kind of merge in the middle a little bit. Anything else?
Ambient
Ambient
lighting.
Ambient lighting. Yeah, there's some ambient lighting. There's one more feature.
Shadow.
Yeah.
There you go. Perfect. The shadows.
Yeah, that's what I was looking for. Yeah, shadows on the bunny.
So I think real quick, like the reason we're asking these questions and the reason why being able to look at an image like this and decompose exactly what's going on is important is because when you're making games, apps, interactive media, whatever in VR, you need to most accurately as possible represent these physically accurate models. Otherwise, your user will perceive it as like fake. I think being able to pick out those aspects that make this image look, quote, real are going to be really important because you're going to have to put them, and you don't have to do the math behind it, but you're going to have to put these features in whatever you make. So that's why that's an important question.
Yeah. Okay. One more simple one. How do we normally represent light in graphics?
That's a big question.
Like a ray.
Yeah, like array. How do you model array? Like, what is array?
It has a start point, it has a direction, and I think it has a length, if I remember right.
Yeah, that's, you remember how to do it, like, mathematically speaking? Roughly speaking.
Not in specific too much.
Yeah, I'm just going to remind people of the array equation.
This is, again, really important for VR because basically anytime you want the user to touch or interact with something, you're going to have to cast a ray from the HMD from the person's perspective and cast it until it hits another object. And that's how you'll be able to tell depth. So that's the reinforcement behind what this ray equation is.
Yeah. Cool. That's my.
Okay, yeah, so I don't have too many formal questions about the stuff that we covered about meshes and transformations. Real quick, I just want to ask a couple buzzword questions. Who can tell me the three components that make up a mesh? First slide from yesterday.
Edges, vertices, and faces.
Perfect. Edges, vertices, and faces. Now, what's the data structure for navigating those faces?
Half edges.
Half edges. Perfect. Okay, who can contrast and compare a BVH and a BSP for me? This is a little bit of a harder one. Is that a hand? Or is that a pen?
Kind of.
Go.
One of them is irregular partitions.
Uh-huh.
And it's because of that, it's harder to traverse the tree and find
Okay.
where the mesh is.
That's good. And what about BVH? Who can help me out here? Who can talk about a BVH, just in general?
It's boxes within boxes.
There you go, boxes within boxes. So you kind of can condense the space the more crowded a box gets. That's the basic example there.
And it's obvious which is a super box.
Exactly. So the traversal is easier, right? You can dive down the tree. There's no weird non-orthogonal lines. Anyway, that's BVH and BSP. Faces and vertices. Yeah, I think that's good. So we can just dive right into, Emily, do you want to do your transformation stuff?
Yeah, sure.
Sorry, you guys are getting rotation of a bunch of different people talking today, so.
So this is going to help you a lot with the first and second questions. I guess an important thing to think about first is that when you're doing transformations that are with respect to local, frames of references, that would be TRS, you're going to be pre-multiplying those matrices. And then if you're doing it with respect to the world, you're going to be post-multiplying that. So that order of transformations is going to be important for your first question. So I guess an easy way to start off is talking about rotation matrices and what they look like. So an easy way to remember, because they're all different for different axes that you're rotating around, an easy way to remember is you can think of this as X, Y, and Z, and you can place a 1 on the diagonal for whatever axis you're rotating around. So this is the Z-axis, and then you can fill in the zeros. And then you can just do this pattern, it's just cosine, negative sine, sine, cosine. And then for a Y, it's going to be different. So do 1 in the middle, and then it'll be cosine, sine, and then negative sine on the bottom, and cosine here. And I guess just to finish it off, X. So hopefully there's you don't have to write this down. You got the intuitive way to remember it, but you can always look these up. So that's rotation matrices. And then translation is super easy. It's just the identity matrix. I'll represent this as a 4x4, and then you just put Tx, Ty, Tz on the sides. The rest are zeros. And an easy way to represent both translation and rotation is by putting rotation matrix in this upper left-hand corner. That's a 3 by 3 matrix. A 1 here, a row of zeros here, and tx, ty, tz. So for the first question, that's probably all we're gonna want for each joint. You can really easily construct the overall transformation by first finding the transformation with respect to its parent, and then concatenating the matrices and by post-multiplying down the chain. I guess could just do a quick example.
Does everyone know what Emily means when she's saying post and pre-multiplying and why that's important?
Oh, okay. Basically, post-multiplying is just if I'm going down the chain for the homework, post-multiplying is I start off with the matrix here, the matrix here, and then let's call this matrix A, call this matrix B and C. Then I'm going to do A times B times C. Does that make sense?
Does everybody see why that post-multiply puts it in world space?
Yeah. I'm basically asking, if I'm asking for the world transformation of this, I'm basically asking, if I'm standing at the origin in the world, then where is this point relative to me? Does that make sense?
So wherever Emily started is her point of reference.
Yeah.
That's the best way.
Yeah. And then you can go over scale, so. Yeah. You're pre-multiplying when we do, so TRS is actually pre-multiplying because that's with respect to local space. So, TRS is the order in which you're applying the matrices. If you want to do translation, scale, and rotation, you want to do it by it's like this in the matrices, but it's pre-multiplying, so you're actually applying scale first, rotation next, and then translation. And the reason why you're pre-multiplying is because that's with respect to the object, not the world.
So when we were doing those graph traversals, starting at the bottom is that way of doing it. And bubbling it. Do you remember when we were just the little green boxes in the slides? You start the leaf node and you bubble your way up to the parent? That's a pre-multiply. You have to do that.
I mean, that's basically it. And their scale, sorry, it was a little out of order. SX, SY, SC. We'll do this along the diagram.
So with the individual bubbling up behind that's TRF. How is that different than finding the world space?
I can go back to that slide real quick and show it as an example. But so you're talking about starting at the green box, right?
That's different because when we're defining these transformations here, this is with respect to its parent, so that means it's local. Does that make sense? And then when I am saying tell me where this joint is with respect to the world, then you're basically just going down the parent tree structure, or you're going down the tree structure and then post-multiplying because I'm asking where am I, if I'm standing in the world at the origin, where is that joint? And then this is basically, you have to do TRS here because you're just applying it when you're at that joint, down the tree structure. Does that make sense?
So the relative usefulness of each one is, the reason we showcase the pre-multiply here is because if you were actually from the rendering side of things, drawing these things out, you would need to know where they are relative to the parent, but if you wanted to inquisitively say where is that object in the world, you would need it relative to the world. So those are the two contexts where pre and post multiplying.
Does anyone want me to rewrite the transformation matrices so you can write them down, or? Yeah. I can just rewrite all of them. So X, you put a 1 in this column here. Think of that as the X column. Or you don't put zeros here, sorry. Zeros here. And then you would put cosine of theta, negative sine of theta, sine of theta, cosine of theta. And that's just shorthand, so. And then for Y, you would just put a 1 here. Zeros along these this row and this column. And then you would do the same pattern, but you would put the negative down here. And then again for Z, put a 1 right here, fill in the row, fill in the column. This is negative, sorry. Sine theta, cosine theta.
So it's x, y, z axis.
Yeah, this is x, this is y, this is z. And then the important thing to note is that the negative is on the bottom for the y axis.
I think also real quick, like it may be useful to, do you guys know what it means to rotate about an axis? Because it's like a weird visualization if you haven't seen it before. Do you know what I'm referring to, like the spinny arrow around?
Yeah.
Does everyone, like, can you imagine what rotating about, like if this is the y-axis, you're spinning in a circle like this? Does that make sense?
Which direction is it?
Clockwise.
Okay.
Yeah, clockwise is positive, right?
Clockwise is positive, yeah.
Yeah. And then z is usually pointing out of the page or out of.
Yeah.
Wait, clockwise, looking from the top?
Okay, so if the ray emanates from a point, it's clockwise with if you were looking in the direction of the arrow.
Looking in the direction.
Yeah, so here's an example. If you have origin and y is upwards, you would go this way.
I think it's a right angle.
Yeah, right. Well,
The thumb points in direction now.
that would be counterclockwise then.
I thought it
Is it counterclockwise? Am I wrong here? Okay, thank you.
Yeah, I think it was the direction of
Yeah, I took,
Yeah.
okay, physics was years ago. Just do this. I don't know anything.
Okay. Any other questions?
So you put up a 4x4 matrix before, which had like the rotation in the 3x3 area. Then
Yeah.
So for each of those, we create a 4x4 and then multiply those together.
Yeah, that would be for like the first question.
Okay.
What I was saying, I mean, it's basically if I represented this as, I don't know, did we go over homogeneous? We did, right?
Yeah, we talked about 4D.
Yeah, so we use homogeneous coordinates for graphics. And basically, if I turn this into a homogeneous matrix and multiplied it, it's like multiplied by some t over here, I would get the rotation matrix up here, and then tx, ty, tz, y. And that's a 4x4 matrix that represents both your rotation, translation, in the right order.
And it's homogeneous so that you can like multiply all three factors through and preserve the state in the 4D version. Does that make sense?
Yeah. So for the homework, you don't have to multiply it out in TRS unless we specifically ask for it. You can just use this.
Wait, what? You just use that?
Yeah, this represents both translation and rotation. And we don't ask about scale in the homework, so you don't have to worry about scale. But if you do use scale, TRS. Yeah?
Yeah, idea was like we don't need to see a Chern matrix row column multiplication. It's more like, do you know how it's represented?
Okay. Any questions?
Could we go over like an example of some sort so that like we can see how you multiply it?
Mm-hmm. Yeah.
Matrices.
So I can show you for local first, which is like when we do TRS. So let's say you rotate first, so then you have like a square, and then you rotate it, and then you move it over, or yeah. Basically, you want to minimize the amount of translation you do, so basically you only do one translation here, so that's why it's TRS. So you're rotating first, and then you're translating. So, and the reason why you do that is because if I translated first, if I translated first and then I rotated, it would rotate like this rather than around its origin. So that's for TRS. And then let's say I have some hierarchy here. So the most important things to pay attention to is this doesn't necessarily have a rotation yet until you look at the frames of references. So you can tell there's a rotation if, like, let's say like the axis was like this instead. This looks weird. So this would be a rotation around the z-axis because the z-axis is like the same, right? And you can tell from like one joint to another if there was a rotation around which axis, because the one that it rotated around remains in this pointing in the same direction. So yeah, that's an important note. So there's not necessarily a rotation unless the axes are different. So and then if there wasn't, then it would just be translation, right? So let's say this is rotated by 90 degrees or 45, so I don't have to do math. So then let's say this is the root, so it's going down like this. This is the root, so let's say it's at the origin. So its matrix would be 1, 1, 1, 1, the identity matrix, right? And then this one, let's say the bone length is 1, so it would be, and it's also rotated, right? So we would do, it's rotated around the z-axis, so it would be like this, and it would be 1 over root 2, negative 1 over root 2, 1 over root 2, 1 over root 2, and then over here it would be translated by negative 1 in the y direction. Can everybody see this? This is just like cosine sine, like whatever, and it's a matrix that, the 3x3 matrix that I wrote up earlier. And then here, so that's with respect to its parent. And then here, we're going to write the matrix with respect to its parent. So it's translated by negative 1 in the x direction. So, and there's no rotation, so it's the identity matrix. Right? Now if I'm asking where this point is or where this joint is.
If the translation is with respect to its parent, would it be in its parent's frame or the world's frame?
It would be in its parent's frame, but we calculate the world's frame by concatenating the matrices in post order. Does that, or, yeah. So we're going like this. So you go this, like let's call this matrix A, call this matrix B, call this matrix C. Then we would do A times B times C gives me the position of this joint. Yeah? Does this make sense? All right, any questions?
Please speak up if it doesn't make sense. Because
what does doing it the other way
Nothing.
So yeah, it's doing the other way gives you nothing about it's okay. Doing it the other way is if you were traversing the actual like tree to draw it out.
Yeah.
Like in the sense of doing the math on paper, it doesn't make sense. But if you're say like there's an algorithm that is at point B, and you're going to C, you would need to take C's matrix and multiply it by where you are at that point, and then you're doing a pre-multiplication.
So C not going horizontal with respect to the world.
I don't.
Along the new x-axis.
Oh, okay. So are you talking about its like coordinate system?
Yeah.
So if there's no rotation,
Rotated by 45, right?
this is rotated by 45, and if there's no rotation from here to here, or from here to here, then this is also in the same direction with respect to the world.
But it's not along the new x.
Yeah, it's not along the new x. So if this was pointing like this, then it would look like this.
So the transformation is still in the real x. Because you just said it's along negative x.
Well, I wrote this with respect to its parent because it's 1 away from its parent, but from the world, it's also that way just because this is a very simple example. Because the world origin is right.
45.
What?
I'm just confused because the parent x is along the 45, but the translation from B to C is straight horizontal.
It's actually not straight or horizontal. Like, I'm defining this transformation with respect to its parent. So if it's not rotated, if it's rotating the same orientation as its parent, there's no transformation that takes me from this space to this space unless it's the identity. Does that make sense?
Sure.
Okay. Is there where am I going wrong here? Like.
Well, because it just looks like from your picture the what's translating along isn't aligned with the new x-axis.
Oh, right, okay, so that's my mistake, sorry. Yeah, okay. So it would be going like, say, I wrote this weird, so it would be going like this. Yeah. It would be going along that x-axis.
Yeah, idea is like you inherit the coordinate system of your parent unless you have a rotation, and then you rotate.
Yeah. Sorry, I realize this is confusing, but the homework should be good. There's probably one little.
And come to our office hours, you want to do it in front of us, we can work through it with you.
Yeah.
That's totally fine.
Any other questions?
Just to like clarify that positive rotation is counterclockwise, wouldn't that one, this is just nitpicky, that one would be the Y and then this one is the X.
We're rotating around Z, right? So that this is Z. You know what? I don't know. I'm sorry. I just threw this up. So in the actual picture, it's like a lot clearer because that's like an actual skeleton structure that has like all the axes like drawn out with all the right orientations and the right translations. So. But the important thing to note is when you're writing out these transformation matrices before you concatenate them is that it's with respect to its parent, right? So you're looking at the parent's orientation and where it is relative to the joint you're trying to come up with the transformation for.
I think the diagram in the homework also has coordinate axes drawn in each joint.
Yeah, it does.
Yeah.
One's a little messed up, but I can clarify if anybody gets thrown off by that.
Okay, so that was a lot of transformation stuff. Before we move on, was anything else confusing? Like, can we redraw anything if that diagram got confused, like crowded? Bueller.
Good.
Okay.
Cool.
Okay, so Trung is going to continue with everything we did yesterday. Do you want to save 5 minutes? They have no talks and scheduling for we.
Okay. Just cue
Yeah.
everything.
I'll let you know. So I put the slide way back.
And you have Unreal.
Yeah. Oh, the launcher is open. You can go from there.
Let me open the launcher first. Okay, on the homework, you guys also have analytical lights. Just want to clarify what the term means for the analytical lights. It's just any light that can be solved through math. So, in an example that I talked about would be point line directional light. Spotlight's not a type, but not area light. It's because those light have like a well-defined mathematical function that can be used to solve. An area light just doesn't have that feature. Just to clarify in the homework. Okay, so I'm going to do a quick Unreal demo for this. You mind if I just create a new project in this folder? Yeah.
Yeah, so if you guys have installed this, as you should have for the survey, we didn't really check, but this is what, you should have seen the launcher that Trung has in the background, and this is what it's like to start coding from scratch. You won't be actually touching this for like 2 weeks, but it's really useful for showing demos in class, so this will light it up a little bit. Also note that, so Trung is running this on my like super beefy MacBook Pro. Unreal Engine like eats RAM like crazy, and is probably going to run slow on a laptop. So don't be like afraid or scared if that happens.
Alright, I'm gonna start with an empty scene, so I'm gonna try to delete everything in this, so it's not confusing. Nothing. Oh, no. Does the delete key not work?
Function delete.
Oh, function delete.
Function backwards.
I see. You know what?
You can control A.
Yeah.
After that.
Oh. Then this guy. Okay. Alright, so without any lights, we have nothing. So we're gonna add some lights into it. Actually, let's add some objects first. So you see that if you don't have any light in your scene, I added a cube. You can't see anything, like a sphere. So this is a sphere in the cube in the scene, completely black. I'm gonna add like a ground sort of thing also. Right here. Oops, that is not supposed to happen.
You should just add a light.
No, did I add a light? I don't think so. Function delete. Yeah.
So the idea here is like, even though the computer, also don't try to use Unreal right now. You'll hate yourself. Idea here is like the computer is drawing a cube somewhere there, but without any kind of lighting system, it doesn't, there's nothing to render there. The same way if you have a really dark room and we have these lights off and then there's no light coming from the windows, you won't be able to see.
Mouse is also not working. It's okay. It's okay.
Sorry for the tech difficulties today, guys.
Okay, I'm just gonna add light. So, okay, so I added a directional light. It's kind of a little bit dark for us to see. So now we have something in the scene that we can see. I want to add a ground so that we can see like a shadow casting on it. Also, oh, you have a mouse? Oh, awesome. Okay.
That's good. Oh,
no, wrong one. Okay.
I hope OBS comes back. Okay, that's good.
Okay, cool. Awesome. Thank you, Alan. Okay, so in this scene, you see with directional light, we have some shadows in the scene now. But the feature of directional light is only has direction. It actually doesn't have an origin. So you see if I move the lights around in the scene, like the shadow remains the same. But if I change the orientation of the light, you see how the shadow changes. So that's directional light. And then let's see. So the lighting is kind of strange right here. Let's add the point light now. So now we have point light. Point light is just a point in space that has a radius, and then any objects within that radius that you see here will be illuminated. Anything outside will be darkened. So we talk about static light versus that's not right. We talk about static light versus dynamic light, or static shadows versus dynamic shadows. You see here, there's no shadows at all. It's because Unreal is not computing any dynamic shadows at the moment. Let's say I'm gonna bake lighting into the scene. It's gonna take a little bit of time, and you will see the lighting condition change.
So when we talked about static versus dynamic lighting yesterday, or Tuesday, we talked about how static lights only are it will only change shadows for objects that are officially marked as static, meaning they can't move. So the stuff that Sean just made isn't marked as like non-moving objects. So that's why you just baked the scene.
Yeah, so you see now, lighting is different. The cube looks a lot better. It's a little bit dark in the back. If I move the light source, okay, let's say if I add another point light, like there's some preview of what the shadow would look like, kind of a little bit on the ground for the sphere. If I bake it again, let me see. This is how it actually would look like in game for that. And you move this object around, you see it's not being updated at all. And then in order to create shadows again, you have to bake again. But it's possible to do dynamic shadow. It's just a little bit slower if you want to do that. Unreal also doesn't have area light. So to demo area light, I'm going to back to here. And 3JS. 3JS has a great example list here. If you go to the example for 3JS, you can just type in lights. You can see a lot of other light types that they have. They have point light demo, and then this is area light, and the shadow for area light is also different in this case.
So 3JS is what your project starting on Tuesday is going to be in. So basically seeing all the content that you're going to be teaching as far as engines for this semester.
Yeah, the examples of 3JS is a good place to go if you want to see some feature of 3JS. It's kind of preview how certain classes are being used and how it looks like. View source allow you to look at the source code that they have, everything open source too. This is the GitHub repo, and you can go to example and then they have everything here that can help if you need to look up how to use certain functions or use certain classes.
We'll be doing a full in-depth analysis concepts tutorials on Tuesday and Thursday next week.
Okay. All right. Now next to camera. Okay. Camera is the only thing that we have to look into our 3D world. It's usually just a point in space, but it has some other features. So to start with camera, camera was the virtual camera that we see nowadays is modeled after what's called a pinhole camera. A pinhole camera is just an imaging device that is usually like a dark room, like a dark box like this, with a backboard. This is usually called an image plane, and this is a pinhole. So everything you see outside in the real world will get projected back into the image plane of a pinhole camera. So we usually start with this model for camera, and then some other terms just so you guys are aware of. This is called an image plane, so that's the outside. This is the inside the box. This distance between the image plane to the front of the wall, this is called a focal distance. It is because light concentrates and focus right here. And this, how big this opening is called an aperture. So what do we do in computer graphics? We take this model and we flip the image plane to the front. So now, usually in 3D, you will have a point like right here. Everything you see in the 3D world gets projected into something with an image plane in front of that point. I'm going to visualize this. So it looks something like this. This is how we model it. Then it looks like something like with the image plane right at this point right here. So this is kind of the screen you're looking at in your on your desktop. This is called a near plane also, and this is called the far plane. The concept we encapsulate everything we see in 3D world into a frustum. So everything that's possible to be seen is inside this sort of truncated pyramid area region right here. So the frustum gives you let's see. So that frustum that we just saw, it calls the perspective for the perspective camera frustum. Going to the different types of camera. Okay, so you see how we can represent that as a pyramid. Look into a point. That gives you like a good depth illusion of how the objects are spaced out. There's some other camera types in graphics that is called orthographic. So in a 2D game, for example, you don't see any depth at all. This is because they changed the frustum to be like a box kind of thing, shape instead of pyramid shape. That's why we have different perspective for different camera type. Okay, so let's say, that's for camera. Let's say you have a scene like this with the camera looking straight at a cube A, and there's also another cube in the back, and cube B is a little bit to the right. What do you guys think, if we looked at to the computer screen, what do you think how the image would look like?
I think the right one would be smaller because it shrinks more. It's farther away.
Yeah, it's further away. It's affected by depth. For orthographic camera versus perspective, how do you think they would look differently?
Oh, was it? I just thought there was one.
Okay. Oh, sorry. Yeah.
Which one is the pyramid one?
Yeah. So the pyramid one is this. That's the perspective camera. And orthographic camera is the one on the left side. So for a scene like this, so you say the one in the back a little bit smaller?
To use that perspective.
Yeah. And what do you think how it would look like for the, actually as someone else, yeah? You guessing what it would look like for orthographic? It would be exactly the same size. Yeah, there's a flat 2D. Cool. So we talked about the Frustum. Let me go back to the Frustum one and draw out a little bit. My drawing just bad. Okay. So this is where the camera usually is really called camera. Another term for camera sometimes people use is called eye. It's the same thing. It's just a point in space. Okay. And then. Okay. So like in this image.
Can everyone see what trying to steer? This is pretty important to the 2 planes.
Oh. Okay. So everything inside. So let's say you have a sphere inside, and a sphere outside right here. Only this can be seen inside the camera because it's the only thing that's inside, encapsulated by the Frustum. And the same thing if there's an object out to the side or behind the far plane, none of that will be rendered onto your screen at all. The camera also has what's called a look at vector, which is just a vector from this point into the center point of the new plane. And it actually would be, the vector would, if you extend this vector out like this, it will also hit the center of the far plane. So that's usually called a look at vector. And everything in the Frustum is symmetrical around this vector right here. That is very typical for orthographic perspective. Some game and some application does something called interesting called oblique perspective also, which is this perspective, but you shift, sort of tilted the Frustum a little bit up, and now this look at is not center right here, but center a little bit lower in the image plane. And that also used for like some interesting effect, sort of like some racing game. people also like play with perspective a little bit to change it. So that objects is on the ground that look closer to you, and objects above, like farther away, looks smaller. Like just exaggerate the effect. So camera give you a lot of little tricks to affect like the visual, how you look at stuff. Okay, so I'm gonna go a little bit, different attributes of the virtual camera. Position, simple, just a X, Y, Z for this location. The look at direction we just mentioned is a vector going from the position into the center point. Typically will be to the center point of the image plane, near plane or far plane. The up orientation. So camera also needs to know which way is up, because you can also have the same position, same look at, but you can also like tilt it down so everything is flipped or something like that. Field of view. So field of view talk is concept of how wide, like how big this angle is for the frustum. In orthographic, there's not really a concept of field of view, but for perspective, we have field of view, which is so if something has a bigger field of view than this, the frustum will be, let's say if I increase the field of view, the frustum now will be like bigger than this, for example. That will encapsulate more objects and things like that. The effect of increasing the field of view is similar to zooming. Now here's the question. What do you think if we make this frustum now bigger? What would happen to the sphere inside here?
I think the object would appear smaller.
Yeah, and why do you think that is?
I guess if the far plane is larger than the perspective of the object would then make it appear smaller, and if we make the field of view smaller, then it would look more similar to an orthographic camera, I think.
Yeah. Can you think of any other? Okay, that's fine. Yeah, it does appear smaller. The most intuitive way to think about it is seeing this is your screen, and your computer screen doesn't change at all, stay the same. So now if you put more pixel onto it, then everything has to squeeze in to give more, like to be able to capture more of the scene. But the screen doesn't remain the same size. Therefore, everything just had to be smaller at that point. Similarly, if the field of view is bigger, and then we have now this sphere right here, it used to be outside of the frustum. We increase the field of view, now we can actually see this thing also. So everything is smaller, but you can see a lot more of it. It's the same thing of zooming out when you're increasing the field of view. The opposite is when we're decreasing the field of view, everything getting bigger, but then it's closer and more focused. Aspect ratio. Aspect ratio, just talking about the ratio between the width and the height of your image plane. So let's say for a VR headset, we have a resolution of 2160 and 1200. 2160 is for the width and 1200 is for the height for both eyes. Because when you have your headset, you have basically a giant screen, but like it's for each eye. What do you think is the aspect ratio in that case?
9 by 5.
You want?
9 by 5 or 1.8.
1.8. So how would you how do you do the?
It's just 2160 going at 1200.
Close. So the screen for VR, the screen is for each eye, right?
Okay.
So you have to divide the width by 2 first. So you get the width for each, because it's basically just each eye see the same image. But you have to divide the 2160 by 2 for each eye. left and right, and then you can do that, divide by the aspect ratio, divide by the height to get the aspect ratio. It's a little bit different from for desktop. Desktop only has one screen, so whatever resolution is for the same camera, but VR is a little bit different in the sense that it has two eyes, so each eye has its own camera kind of concept. And we talk about near plane. So, what if I move this near plane to be over here? Like, oh, well, if I increase the distance of the near plane past this sphere, what do you think will happen?
Why
Yes.
do you need two things, like one screen each time?
Oh, yeah. It's actually one big screen in the headset. It's like a long big screen like this in the headset. When you put it on, like this eye is actually divided by two. So this will be your left eye, and this is your right eye. Because each of the eye perceive, you can close one eye and then see different things, and then it's like slightly off the perspective. So it's like imagine you have two camera. Well, that's kind but each eye has a different frustum. It see different things. So you close this eye, you see more of this side, and then your left eye see more left, and your right eye see more right.
So VR there's two cameras.
Yeah. So in VR, actually, there's two cameras. There's a lot of tricks to use the same camera, but just kind of rotate it or offset it. But in a headset, they just use one piece of hardware, just a giant screen. Except when it's kind of divided by two, like this. So this is 2160. This is 1200. Then you actually only see, you have one camera on this side, and this camera will have an aspect ratio of 2160 divided by 2 divided by 1200, and this one has the same. Yeah. It's a special case, and then if you have 3 eyes, then you've got like 3.
So, given that, what Trung just drew, can you imagine why a Google Cardboard has like way lower res than a Vive or an Oculus? Anyone?
And then maybe that your phone has like less pixels in it.
Perfect. Okay, this is a Retina iPhone, so it's a little bit different. But if you have an Android phone, and you're splitting the pixels in two, or splitting the width in two, you naturally will have since you're squaring, you should have a quarter of the pixels essentially, right? So it'll look lower res. Does that make sense? Yeah, no, someone. Yes, okay, saw not, thank you.
Okay. Do you guys have any other questions before I move on to the next slide?
So what can you, I would assume if you change something about maybe the near and the far plane, your perception of the depth would be different? Is that true?
No. Yeah. So perception of depth would be the same. Just imagine from this image that you move this back. You don't see. So let's say I move this past this sphere. You just don't see that sphere at all. But the angle is actually what makes this feel perspective feel different.
Okay.
And we talk a little bit about when you tilt, let's say the look at is now not centered, the middle point of the image plane is centered a little bit lower, then you get, that does change the perspective a little bit also. More it's kind of cut out a little bit here. Yeah, it's more about the angle of it. In near plane and far plane doesn't do anything. The thing to worry about near plane and far plane is, okay, so let's say you have a forest. Let's say you build a forest, and then you have 1,000 trees over here, right? A lot of trees in this scene. But so far away, you actually don't really care you see on those trees at all. It's you actually just want to say, I don't care about the one in the back because it's so far away, I can't really see the tiny. What you want to do is actually want to use the far plane to kind of chop all these trees in the back away so that the graphics engines just have to do less work. It can just like, I don't care about this, I don't have to worry about to compute its shape, to compute its color. I just cut out the amount of work I have to do. So you bring the far plane closer to you, like that. That's an example of how you want to manipulate far plane. Or if you don't see objects so far away and you really want to see it, then you want to move the far plane back so that you can see, like, you want to see birds flying or something like that, and it doesn't show up on the screen. That's when you want to manipulate the far plane. The same token goes in your plane. If if you model characters and it has like an artist happen to put like a helmet like so close to his face, and you just I don't want to have this thing blocking my vision, you can just increase the new plane and just kind of cut it off and chop it out. So that's sort of a different reason why you want to manipulate them to include or exclude objects inside your scene. Yeah. Any other questions? Yeah.
So in the Pinhole camera, the focal distance is between the image plane and the aperture. So what is it like here?
Oh, it would be, it would be actually 1. Okay, that's just a convention. It would be the distance between here and, well, it's a little bit tricky because there's a step called like normalized device code, like to bring stuff into camera space. We normalize it down to 1 eventually. It would be this distance right here. But in graphics, there's a little bit of math before they transform all the object in front of the camera. Okay, we talked about transformation. Let's say everything is in word space. And the camera also has a position, right, in word space. But in fact, when we want to display on the screen, we want to bring it into something called the screen space, which is 2D, right? A couple of steps is, so you go from word space, and you want to actually bring everything. So instead of moving the camera, instead of keeping the camera in word space, what you want to do, you want to bring everything else back into what's called a camera space. So this, let's say this has let's say the camera position is, I'm trying to think of what's easy math. In word space, the camera position is 0, 0, 1. And in word space, this sphere right here has a position of 0, 0, 5. Just a simple, like this is the word space position of camera in the sphere. We actually want to bring everything into the camera and make the camera the origin of everything else. This step you guys don't have to worry about because it's what the graphics engines handle underneath. But what they do is they bring this object into camera space. So now this sphere, so in world it's like this, but in camera space, this position is now 0, 0, 4, right? Because the distance between the camera and the object is only 4 along the z-axis. You bring into camera space, and I do something interesting that convert this. That now this first term right here, there's another transformation that normalizes the sphere, the first term to be like a box that's going from -1 to 1, like this. Like this first room right here, they take this corner of the first room like this, and they normalize this to something like a small box. And at that point, you have an interesting thing like the camera position is there, and this focal distance is now become like 1 or something like that at that point. And that again, the reason for this is it also makes it easier to convert from every point on this. They can easily transform that to the screen, like the pixel value, and then which determine which pixel we display on the screen. All that step is going like underneath with the graphics engine. It's being handled like that. So the focal distance started like this, but then eventually when you do math later on, it's just like normalized down to 1. So I go to like this. So there's some transformation to bring objects into screen.
It's a really complicated matrix.
Yeah.
If you want to look it up, it's called the projection view matrix, but like it's a lot of work. I don't think you will have to play with. So when you change the camera attributes, the near plane, far plane, field of view, that would change this step right here, like how stuff looks on the screen. Okay. Any other questions? Cool. All right. So I'll just go to camera demo. Yeah, it's easy to see it. Then to just talk about it. Okay, let's find camera. Where are you? Yay, camera. Okay, so this camera this mesh that you see right here is actually does not exist in game. Just don't be confused. This is just Unreal showing it to help you locate where the camera is when you're editing. But when you're in game or when you're in the application running, the application should not be there. It's just a point right here. So I'm putting the camera right here, looking at the. Can you guys see it all? Maybe it's a little too small. I don't know if I can make this bigger. The preview?
Yeah, the preview.
I don't think we can.
Okay, well, yeah. So as you can see, I can rotate. Move the camera. It's very simple. There's things change, move far away. Okay, and we talk about. So if you see how there's depth on the cube right here. You can see the side of it. It would change this to orthographic. It's squished into basically it doesn't have a depth concept anymore. It doesn't matter. You move back and forth, it's still the same. You move behind the object now, it just disappear. But you can still move left, right, up, down in orthographic just to see the object. But you really don't see the side of the box anymore at this point. And you can change it back to perspective, and now you can see the depth of it. Field of view, so increasing the field of view right here. So you see object gets smaller and it's kind of squished a little bit toward the end also, like converge at the horizon. When you increase the field of view, you see a lot more of that ground plane, and everything is just tiny. And then decreasing the field of view makes the object gets bigger and bigger, and then you focus on it's like zooming in. And you can actually also go negative, but I don't recommend you going negative. I'm not quite sure what you see. You see like things inverted and stuff like that. If you go negative for field of view. Aspect ratio. So it's basically the screen size. So you can typical screen size thinking 1.6 or 1.8. You can change the aspect ratio to make your image wider, or more squarish. So aspect ratio 1 is just width equals to height. So this box, this preview, now showing exactly that. Anything else? Let's see. I'm sure there's a way to change the near plane and far plane too, but I don't see it here. Okay, well, I don't see it there. So anyway, okay. So that's the camera. Ira? No, so let's just try it. So with inside orthographic, and you just don't have that options anymore. But yeah, you can change the width and height of the orthographic though. Like, yeah.
Also, if you can tell the camera is like doing some weird like light adjustments, that's Unreal trying to mimic the way your eyes adapt to dark rooms. So it wouldn't.
Oh yeah. It's some fancy.
Really
fancy. But there's also a new cliff. I don't know. It's so hard to see here, but this is a new plane distance for orthographic, and then this is the far plane distance for orthographic. But yeah, I'm not sure why perspective doesn't have it. The typical value for you can be saved to use typical value I usually use is 0.01 for near plane. And for far plane, I usually just go 1000 like this. That's in general is a good just to start with. If the camera doesn't have that, but most cameras you instantiate inside an authoring tool like Unreal 3JS will give you some good default value to start with. But that would be like the typical range. Okay. Okay. Got 10. Yeah. Okay. So depth of field. Just throwing you guys out. So these are some of the post-processing effects that you can add from the camera point of view. Depth of field is when you sort of changing the focus and the aperture to give you more light into it and only focus at certain points. So optics is like kind of at this area like sharper, and optics further like blur out. Pretty cool effect that you have, and that's done also using the camera attributes. Also, there are other tricks to mimic this ability, this effect without actually modifying the camera attribute. You just can modify the pixel directly. Motion blur. So this cube right here is kind of rotating, and you see when things are moving, just blur out. So that's called motion blur. Bloom just make things shinier. Yeah.
Cheap way to make your Instagram look.
Yeah, I'm not a big fan of bloom, but some people like it. So it makes it kind of cheesy. Alright, so that's it for camera. There's more post-processing effect, but we can talk about later. So moving on to textures. So textures, these are some samples of textures. Basically, what is texture? It's just a 2D array of data, usually for contain an image. That's the most typical use of it. It also can contain multiple images, layout and stuff like that. Usually your mesh will have no color at all when you model it, and you use texture to kind of apply on top of the surface, so you make the surface look better. So in this case, they just put a texture onto his face, and now he looks real, well, more real. But it's really just like a container, a buffer of data, typically used for images in graphics. So different type of texture. So this is called albedo or diffuse matte. Usually it's a color texture. This is a sphere, and then the texture is just like a square image right there. And you map the texture on top of the sphere and give it the color that it wants. Alright, normal map. So okay, so we talked about lighting before. I'm gonna erase this part. Okay. So we talked about lighting before. Let's say you have a surface, which is just a plane looking like kind of side view to the plane. There's a sunlight, or there's some light source right here that has a ray onto the surface. And let's say you want to figure out what what color or stuff like that it will be here and how the light will be reflected. There's usually a surface normal that go out like this, and then this will tell us using Snell's law, which is really old in physics. Tell you that this will be reflected some angle like this. This is the reflected ray. Now, so for example, let's say the light is up here pointing down. There's another light up here pointing down, and a light. Actually, I just do the light up here pointing down, straight down, directly at the surface normal. Versus there's a light at an angle like this. What do you think has more, like which one is brighter? Which light will make this surface points more lighter, like more brighter? The one that's pointing perpendicular to it, or the one on the angle? Yeah. Yeah. Do you know why? Yeah, it's like you kind of imagine like there's some energy of light going down and like this, and then all the energy is now focused on this. This area is like a little bit smaller. So let's say you imagine light is like a bundle of ray coming down. There's some small area right here. Now let's say the same light, but now you shine it at an angle like this. You have like a bigger angle at the surface, but it's the same amount of energy going down. So that means the density of the energy, like how much photons is on the surface, had to be distributed on a bigger area. Therefore, makes the intensity of the exact one point a little bit small, like less than going perpendicular. And all this to figure out how much, like this angle is something that people usually use surface, use a normal like this to figure out what's the angle. If the normal is directly opposite of the light direction, then you know that you have full intensity at this point. And if the angle of the normal versus the light is like 45 degree, or if it's 90 degree, if the light is right here, and you compare the normal, and you have a 90 degree, then you know that you basically receive almost like zero light intensity at this point. So normal is a good indicator to tell how much light energy that we get on the surface point. In computer graphics, normal is actually not always perpendicular to the surface. So we say that we can cheat by, if I have a flat plane like this, but I actually want to make the intensity of this a little bit less in my computation, I'm going to reassign my normal to be like this, to lie to my math that now I have less energy, receive that point, to change the shadows and some of the other tricks. So they come up with an idea called a normal map, which is basically an image that has a bunch of these fake normal at every single point, like this. So that when you do lighting computation, you can just play around with how the light intensity will look like. So this image right here, which I took from Adam Malley, who's teaching 460-277. This doesn't have any normal mapping, but you see this little fractal thing on the donut, on this donut. This is after you apply normal map. So you say, like at this point, there's some fake normal that's not perpendicular to the surface that allow you to, lighting now it's just been tricked to do something different. So it's really cheap. It's not a real geometry. It's just an image, a texture, a 2D texture, applying it, and give you a good illusion. Unfortunately, we have a problem with VR. Is user in VR can actually look closely and certain stuff, they can tilt their head, and they can walk. Let's say they walk up to this model with the headset, they can actually look sideways and check to see if there's any geometry coming out from it. Easily to tell that it's fake. So a lot of the time, normal map actually doesn't work in VR very well. There's something else called parallax mapping. Some other kind of texture that you can apply on the image to help, but typically we just want to use real geometry in that case. You want to actually fake the bumpiness of a surface. Also, just to clarify, texture can be layers. So we have a layer of diffuse texture, which is the color of the model, and the normal map is another layer on top of it. So texture can have multiple layers. UV mapping. So in order to tell so we start out with a square like this, and in order to tell on this point, which textual element should I use, we use something called UV mapping. So, for example, like a box like this, imagine this is like a texture. So this flat right here you see is a texture. UV mapping kind of tell you this point on the surface of the cube should be mapped to this color or this portion of the texture. For example, like this. This process called UV mapping. Also, again, just bringing this up so you're aware of this process. You guys also don't have to actually do UV mapping. This is more like an artist job than programmer. The concept you should be familiar with.
It's extremely tedious if you're an artist.
Yeah, it's extremely tedious. You kind of like tell like this part go here and this part go here from the surface. So as you can imagine, like this model is just a lot of work to like do UV mapping from the texture to the surface. And the reason it's called UV is because the coordinate of a texture is, instead of in X and Y, they use U and V, so that we're not confusing with the actual model that we're using for X and Y. There's another very classic example of UV mapping is the Earth. It's a sphere, but we see a map as a flat plane, and that's basically a UV mapping. Like how do you map from like a flat like map to like a sphere? And what they do in there is, so this is their strategy of UV mapping. So you have the Earth right here, and then how do you convert that into this? What they do is they say, I'm going to take this, I'm going to fold it into like a cylinder like this, and then for every point on this sphere, I just project, like I just use exactly like orthogonal projection outside like this, and then for this point correspond to this point on the map, for example, and that's how I get like this map. Okay, I don't know how to draw a map, but yeah. But this is a very classic example of UV mapping. Also causing a lot of problem with like how Antarctica is like giant, just because there's so much stuff. Like it's essentially a tiny spot right here, but it covers so much like surface area for this, so that it makes like Antarctica, like, oh, what's that? Antarctica? No, bottom.
Antarctica would be on the bottom.
Oh, Greenland, yeah. Greenland is the one that gets giant just because of this skewed perspective of how they do it. So
like Greenland is bigger than North America on some maps, right? You guys have all seen that Great Northern Exaggeration.
Yeah. So if you actually want to see the sizes of countries, you should use the sphere itself instead of this, because this is wrong. But
so I think we're out of time.
We out of time? No.
Yeah, so we're going to call a little audible on the homework because Chung and I have like 30 more slides here. So there's a lot to get through. As we said in the beginning, like, bear with us. We're trying to condense a full semester of material into like 2 weeks. What we'll do is the graphics homework will not be due on Tuesday. It'll be due on Thursday. And if you want to take, I think I said on the website, you can take 2 late days for up to 75%, which means you can submit until Saturday from Thursday, and you can get 75%. We're going to get through the rest of the stuff on materials, textures, graphics pipeline, and whatnot on Tuesday. Also, we're going to be starting 3JS next week. Keep an eye out for that. Last thing, if you go to PennApps and you prove to me that you were at PennApps, you'll get 5 points of extra credit. If you go to PennApps and you do a project in VR and you show me that you submitted a project in VR, or at least attempted something, you'll get 10 points of extra credit. So you guys should all go.
Wait, just going, or?
If you go and get a t-shirt and don't do anything, you're not going to get any points. If you go and try something, you'll get 10 points. If you go and don't try something, you'll get 5. So be aware.
I guess we have to run over.